What a
That's definitely an intellectual property violation.
charging. Yeah, for sure.
So you just have to split the profits with the under like $6 a video. Gets
Yeah, but like the saturation gets all wrong.
You give them this giant envelope of cow. Yeah, your profits, your proceeds.
From Hunter solely.
Other people.
What would be funny is if people start, if just everyone's watching the lecture on their phone. Like I can't see that from the back of the class, so people are zooming in on Twitch.
It's just you in here. Everybody else is paying to watch it. Everybody else is just in the room.
And I'll just relay the text chat, like people commenting.
So,
if you want to ask a question that costs $1, it'd be funny.
Unless you just turn it into a long class anyway. They just say, okay, we'll make it all fire. No, exactly. But you're paying to watch these videos anyway.
Oh, and I was thinking about our project, like, it sounds like, from what you've done, you're way more qualified than I am, especially like solo stuff. It's like, I don't care if it's something where, like, we should switch roles or anything like that.
Oh, I mean, so I'm average at like SolidWorks stuff. I can just run a lot of like stressful stuff.
Watch it be like, so I'm really disappointed in your guys'
So if you feel more comfortable with like CAD creation, then I can run.
So the average was a 5.
Yeah, because I know, like, they all know me, so they're like, oh, okay, well, Lucas will give me the CAD, but, like, hearing what you... Yeah, because from hearing what you talked, it was like, oh, wow, he's got a lot of experience that I don't have.
No, just like listing out of the mic.
And it would be cool to learn it, like, if you're open to, like, letting me sit behind and watch.
Oh, yeah. Once upon a time, which I don't think it's going to be a lot anyways, because I went through like 5 hours of just doing one clip yesterday. I think it'll be a pretty easy instruction.
Check it out. There's stuff you know and stuff you don't know, but you may not know that the stuff you know, the stuff you think's cool, the things you do for fun's sake is the stuff that someday could change the world. Here's Mick, who busted up riding skateboards, texting, fragging peeps he doesn't even know, but you know what he's really into? Airplanes. Big, small, wide, rad, sick airplanes. Mick builds model airplanes and other types of flying objects using his ingenuity, going nuts determination. Little does Mick know that this let's do this for fun's sake hobby involves freakish terms like inertia, energy, and Newtonian laws of motion. Using the 4 forces of flight, thrust, lift, weight, and drag, he's able to build an airplane that will make you pee over heads. Who would have thought that something so random like airplane involves so much math or science, and that someday it can take off and land you a gig as an aerospace engineer or any number of jobs to do it for reals. So there it is. Hopefully you'll go nuts on step 2 and do stuff for fun's sake to change your world. The stuff that's the right stuff, the stuff you dig, man. Do it.
All right, so that's our introduction to class. I'd like to show you a video link. Sometimes it's relevant to stuff we talk about. Other times it's so we'll see how that goes. So let's go ahead and get started. What I want to do is just kind of a lay of the land, since I know there's a bit of surprise on Monday. First get the quiz, and then do the teams. I'm going to save a little bit of time for questions, so I'm going to ask my conspirator in arms, Dr. Avery, to give me a 10-minute warning. So say about 3:10 or so. So we can wrap things up, do a little bit of a hot wash, and then take any questions you might have on the way out. So, welcome to Applied Aerodynamics and Performance. So we'll talk about the content of the course in a few minutes. First, a little bit about myself. So I have a bachelor's degree in aerospace engineering, my graduate degree in mechanical engineering from Mustang. My favorite class to teach is this one. I'll talk about why that is in a minute. Some of the things I like to do, reading, hiking. So on your surveys, I did ask you just kind of get a feel for your personality. One of your favorite movies from last year, mine was Jojo Rabbit, favorite TV shows, current ones. So I know Watchmen's now over, but it's still one of those things that spends a lot of time rattling around in my brain trying to figure things out. And a good place. So a little bit about why this is my favorite class to teach. If you look at what I do on the research side, I do consider myself, a true aerospace engineer, so I have just a bachelor's degree in aerospace engineering. Most of you in here will end up with dual degrees. Right? So you just have two of them in your transcript, and then you will have both of them. Diplomas hanging on your wall, so you have both aerospace and mechanical. I'm really, pure aerospace engineering. That's really important for me to get that, because that's what I'm passionate about. Now, what I do on the research side really can be grouped into two generic areas. One is on the fluid dynamics side, and that's where I spent a lot of my early research days in, but I still spend a lot of time doing basic fluid mechanics type of research. And the other is on system design, and that's pretty broad. By system design, we mean, well, we're designing something to solve a aerospace-related problem. Some of that spacecraft design, most of that's related to unmanned aircraft. And this class is really an overlap of two of these things, aerodynamics and aircraft design. So we have both of these things in there. So we're going to be talking about applied aerodynamics a lot. So taking the fundamental stuff that you learned last semester and figuring out how we apply it to one of these things, an actual aircraft, and then spend a lot of time doing performance analysis. So that's where the performance piece comes in there. But to really do that, we're going to be doing an aircraft design as part of that. So that's where your semester design project comes into play. Okay. So Alyssa will give an introduction to herself on Friday when she comes in. I'll tell you a little bit about her. So you've already met our PAs for the semester as well. Most of you should know these from last semester. One of the reasons I asked these three to basically stick on is because they are new, so basically time working as a class. Okay? And you already know them, and they TA this class before as well. And so most of the time that you're going to spend with the TAs is not so much on homework. The homework is actually pretty easy in this class. It's going to be a design project, asking questions about it. We're trying to design this aircraft, and you have no idea where to start from. And they'll help you through that process a lot. So make sure you ask them questions about that. Okay? And we'll come back and talk about that later as well. A little bit about class administration. So we'll kind of hit each one of these in a little bit more detail. First about the text. Were there any text in the bookstore? So what they have there? All right, so this one I put online, and I believe you used Anderson's text last semester for aerodynamics. He no longer, I don't think this is any longer in print, so I don't even know if they have this one there, but we have it as a PDF, so that we can just, it's already on Canvas, so that we can use that. That's going to be our primary text for the semester. It is one of the few textbooks that does a pretty good job of saying, well, here's the basic applied aerodynamics, and then focusing on the performance section. We will come back to this one. We used to use this one when we just had the applied aerodynamics and performance without the fundamentals course, because that spent a lot more time talking about fundamentals as well. But we always felt, ever since I started teaching this course now, 3 years ago, that we crammed too much. Class, and that's why we broke it up into. Now, if you're going to call yourself an aerodynamicist, I recommend you keep on your shelf. It will probably be useful if you particularly are on the aerodynamics sub-team this semester. Well, it's quite around $1,500. That's still a pretty good deal, right, compared to your typical $120 to $250 textbooks. And it's considered essentially the Bible for airfoil design, so really good from a fundamental perspective. Whenever we pull homework problems out of the text, they're going to come out of this. Okay? But we'll also have a lot of homework problems that are going to be custom made as well, particularly for the first homework set, which we'll talk a little bit today as well. So first off, about this course, what do we cover? So this is the syllabus definition. We look at applied as opposed to theoretical aerodynamics, which is really what you spend most of your time on last semester. Take the fundamental equations and you'll learn how to predict lift, drag, and moment on an airfoil and then on an theoretical. Now we're going to take all that and apply it to aircraft design. So we're going to be doing much less prediction. You know, we're not going to pull out the Navier-Stokes equation. Primarily just, hey, here's a curve. You know, let's figure out how we use this on aircraft design. Okay. So, but we are going to be looking at the generation of the aerodynamic forces of flight as opposed to this much more complex beast right here. Right? Rather than just looking at a single wing, when you start sticking all this stuff together, how do we actually come up with an accurate prediction of what those forces are? Then what we're going to do is look at performance. What do we mean performance? It's any question that we ask about the aircraft is how well does it do this? How fast does it go? How slow does it go? How far can it fly? How tight can it turn? All those things are performance predictions. Those are really important from an aircraft design perspective. You're always going to have a customer on one side that's looking for a certain set of performance requirements. So you have to be able to predict those before you ever start manufacturing the aircraft. And that's actually really challenging to do. The aerodynamics, even though it's harder from a theoretical standpoint, we've got down pat pretty well. We can do a really good job of predicting aerodynamic forces. Performance is much more nuanced, right? So lots of things you can do to an aircraft that change how it's going to perform. So we'll come back and talk about that. Now, this really covers both aerodynamics and aeronautics. So it has some semantics here. We talk about aerodynamics, that's just the study of our forces, and the difference between dynamics, right, and kinematics is in dynamics, we're looking at what is actually causing those forces, because those are important to us. And aeronautics is the study of design and analysis of the actual vehicles themselves. You don't necessarily have to be an expert in aerodynamics to do this piece. You know, as a pilot, for example, you spend a lot of time talking about aeronautics. But if you're going to design it, then you better have a good idea about the aerodynamics of it. And then finally, since we're engineers, right, we're designing aircraft, we're also going to look at this from an aviation perspective. And what do we mean by aviation? What's the customer going to be doing? How's the vehicle going to be operating? What's the regulatory environment? We can't design a vehicle like that. We have to understand what that environment is going to look like if the vehicle is going to actually operate in. All right. A little bit about grading. The homework, weekly quizzes, and those are primarily going to be online quizzes, just mainly. Are you keeping up with the material? Just do some very simple questions. Occasionally we'll do stuff in class. Maybe we'll be kind of back and forth class participation. So the quiz like you got on Monday, that's going to be pretty rare. We're going to have 3 exams, which are going to be broken down into an exam focused on flight aerodynamics, an exam focused on performance, and an exam pulling all this stuff together, looking at design performance of an actual vehicle, and then your design project. You'll notice that you're kind of split up into the project's about 1/3 of the grade, and then the homework exams are about 2/3 of the grade. Recommendation, do the homework. Okay, it's pretty easy. It's going to be weekly, so the first one's not going to do until next Friday, because of the holiday on Monday. It doesn't take a whole lot of time, but just do it. In this semester, when people come up and say, hey, you know, didn't do what I thought it usually comes back to me. So just go through the process and make sure that you actually do that. So that's our first tip for success. Make sure you do that. Second is keep up with the design project. We'll talk about the scope of the design project in a few minutes. It's going to be a lot of work, and that's where you're going to spend most of your time in this class, is really focusing on that design project itself. Okay? Main thing is keep up, right? Make sure you have weekly meetings. Everyone knows what they're going to be responsible for on a weekly basis, and you're communicating with the team. Design projects usually fail, not because you don't know what you're doing, but because your team has poor communication. Doesn't matter how you're doing that communication, whether it's in person or electronic, you just make sure you have to have a communication mechanism that works with that team. And last thing is come to class. Right? Primarily, this is where I'm going to share the really important stuff. There's going to be stuff you can learn on your own in the book, and everyone should this point, be able to take the book, read through it, and figure out how to do it on your own. Primarily in class, we're gonna be sharing stuff that's not necessarily in the textbook, but also highlighted things that we need to use. Okay. We will be doing some interactive activities as well. We're gonna have some hands-on projects throughout the semester, apply some things, do some stuff, so it is interactive. I do encourage you, if you have questions at any point, just let me know, right? So even though at the end of the semester, end of the class, we're gonna tend to focus on that, so, you know, if you have something general, you can save it till the end, because we'll try to do that every class period. So we kind of reflect on what we learned, but if you have something that's confusing, you're probably not the only one, right? If you have a question, most likely, at least a couple other people in class, the majority of the class has the same question. Okay? And sometimes that may be because it's a complex topic, sometimes maybe they just don't teach it very well, right? So we want to make sure we kind of get that across, right? I do encourage you, right, when you're actually here, pay attention, okay? So it's easy to kind of get distracted and go off on your phone and do other stuff or daydream. I'll try to keep it as interesting as possible. Now, first homework, this is going to be due this Friday. This is an opportunity for me to learn more about you. I have this on Canvas. You can download the template, draw a picture of yourself in there. Can be serious, can be humorous, whatever. Just as long as I can place a face with a name. I'm really bad at that. So this is here to help you. Dr. Abraham also like that. So yeah, so there you go, right? So I'm surprised that I get it right. And then, you know, information about you. So this is not only helpful for me, but also for your teammates. Because you may have new people on your team that actually don't know much about. So this is not going to be shared with your team. Okay? Now, this will not be the hardest class this semester. What do you think your hardest class this semester is going to be? It's probably pretty hard, but it's a lot of math now. Okay, so you actually, that's one of those classes where you come in and you say, whoa, I didn't know I was actually going to use calculus for stuff. There you go, right? You're already into it. Exciting. So, it is. Differential equations are a pretty amazing thing, right? We will actually use them to a low level in this class. We're not going to focus on them at the end of the semester. We're going to throw some stuff in and do some stuff. We talk about nutrient and energy performance. So I guarantee you this will not be your hardest class for materials. And it's not going to be, probably not going to be the busiest one either. Anyone taking the measurements? Yeah, that's probably going to be Dr. Connor's going to give you lots of work. Now, that's not to say you won't have a lot of stuff to do on the project, okay? But this is what I consider to be your most important class. Why? Because it's going to serve as the foundation for the courses that you're going to take later on aerospace engineering. So where are we at right now? We've taken this one. Okay, if you're in here, you've successfully navigated Dr. Davis. Right? You made your way out, right? So, my goal is to make sure that everyone in here makes their way out to this one, right? Right? Because it is incumbent upon you to make sure you do that, right? If someone ends up getting a D in here, or F, it does happen, it's because so it's really going to boil down. So this one feeds directly into the Pilot. Now, this serves as the foundation for the Big Three courses. Okay? Because everything you're going to do in the Big Three, aerostructures, propulsion, performance, and stability control, are based on stuff that we're doing in this course. Now, what that does is this kind of looks at the vehicle from a pretty holistic standpoint. It says, hey, I have aerodynamics, I have structures. I have power plant on here, I have some control systems. How well do all these things work together to form as a system? Okay, so we're gonna think a lot about system engineering. Think about that from that perspective. Then what you do is you do a deep dive to these topics. And we're pretty unique. I think we're the only university that does that, where we have a singular project that spans all three of these courses. So that way you're gonna learn the basics this semester and then really get deep into the next semester. That gives you an opportunity to start to think about your specialization in your career. What do you really enjoy? Is it going to be the aerodynamics? Is it going to be the propulsion system? Is it going to be the structures? Okay. All those are important. You probably won't be doing all three of those. And then finally, you take that off into the Aero Lab and your capstone. Okay. We're also pretty unique in that we try to give everyone a realistic flight test experience. So it depends on how busy the aviation school is for any particular semester, on how easy it is for us to schedule flight time for everyone. Here this semester it's a little hard to do, but we do have a really great simulator that we use for that experience as well. Okay? Because we want to make sure that you're not just designing an aircraft on this paper, that you start getting an intuitive feel for how the aircraft works. Okay? So it's really important to us that you leave with that. And that's one of the things that makes OSU really unique, is how we structure it. Okay? We fight really hard to make sure we retain this, even though there's a lot of expense how to do this. Now, let's step back a bit and now look at all these different kinds of aircraft that we have. And we're going to use the word aircraft a lot this semester, and that's a really broad term. There are a lot of different types of aircraft out there. Fixed wing aircraft, rotary wing aircraft, and lighter than air aircraft. We're going to try to talk about at least each of these a little bit, so that way you have a broad overview of this. But our focus is going to be on the conventional airplane configuration, right? This right here. Why? Because that's 99% of things that are actually flying out there. And most of you actually end up staying in the aerospace engineering industry. If you work on the aircraft side, or the spacecraft side, that's most likely what you're going to be working on. These tend to be for specialty items. Everything we learn over here can be applied to these. They're a little more nuanced details than how operate. Now, how we do this in terms of our focus is through this design project for the semester. Now, your deliverable for this at the end of the semester is a 100-page report by a maximum of 10-person team. Okay, so I think our maximum at the end of the semester is 9, so it actually works out well. The optimum we found over the years is 8. Okay, if you get actually 10, you end up having a couple people that can kind of hide in the shadows. Not really good as much as they should. Now, 100-page report. Does that sound big? Sounds a lot? So here's how you're going to break it down. Actually, there are going to be lots of pictures in there, and there are going to be lots of plots and charts and tables. Okay? But think about it this way. How many weeks do you have in this semester?
16.
If you do, if everyone on the team does 1 page material a week, not only do you have 100 pages, you have more than 100 pages. Okay? That's what you need to have in your mindset right now. That you're not waiting until deadly to write 100 pages. That's why you're actually going to have 2 progress reports throughout the semester. Progress report 1 is going to be the first third, progress report 2 is going to be the second third. And then you fill in the rest of it. Okay. And usually what I find is that first progress report, teams usually put in somewhere between 40 and 50 pages on that first report. And so that's halfway there to get to the 100 pages. Now, also that 100 pages, I'm not grading on the team, I'm grading on quality. So if you do a really good job on 7 pages, it's fine to effective grading. But you want to make sure you have everything in there. And it's really hard based on everything that we're doing with all the subteams, all the materials we're going to have in there. It's going to be hard to include all of this stuff in there if you don't have kind of that full phase, okay? So we're gonna come back, we'll spend a lot of time this semester talking about all these different things. Some of it's gonna be this semester, some of it's gonna be front loaded. We're gonna spend a lot of time on this. Okay? And what we'll do at the end, right, we have 2 separate design projects in here, is, I actually have the other aero faculty kind of judge and rank those. So we'll essentially have about 5 projects for each of these 2 design concepts and say, hey, which one, if this were a real competition, would you choose as a winner? Okay, that won't affect your grade, but it will affect your grade. Now, these are the paragraphs you already have seen. You're gonna have lots of questions about these. We'll come back and talk about this. So you'll actually get your first assignment. Dr. Avery will talk about that on Friday. In terms of benchmarking, you can start thinking about this now, where you're not gonna be doing any real physics. All you're doing is getting data about every aircraft that kind of fit in these types of categories. Because one of the best ways to design an aircraft is to look and see how it's been done elsewhere, right? So we're gonna spend a lot of time thinking about how we go through that design process and why we do what we do when we go through design. Now, here's some examples. These are all previous design projects from various semesters in the past. So this is one of the ones from the last semester. They were doing linear inspection by UAS. Transport aircraft, 2 down here. These were actually different semesters, different design projects. And then a large unmanned cargo hauler aircraft. Okay. I think it actually was. That was Woody's. Yeah, Woody's the team. Yes, there you go. I didn't even plan on that. Yeah, so this is Dr. Avery's first. It's like, what, 10 years old now or something? Yeah. So we do have pretty high expectations. So the designs that come out, are usually pretty good. And this is an opportunity for you to really start saying, hey, why do I want to be an aerospace engineer? To design cool stuff. This gives you an opportunity to design cool things, right? Now, kind of going back to how we design stuff, how we're going to analyze things. When we go through this process, we're going to spend a lot of time talking about basic fundamental type of sciencey topics, as I call them. Aerodynamics. You take a wing, you put a flap on it. How does that work? Propulsion systems. It's not going to be a deep dive into this, but it's going to be enough that you can understand the difference between how a jet engine works, how a reciprocating engine drive propeller works. So we can make educated decisions about which one to choose. So, these will take up about 2/3 of the class when we do that. But for this design project, we're also going to treat ourselves like traditional design engineers. Because if you're sitting in Boeing, for example, you're not going to say, hey, we're designing the 797. I'm going to start from scratch and just go to basic theory and start designing from there. No, I'm going to use what I already know about the other aircraft. Okay, what to do, what not to do. Okay, we're going to spend a lot of time talking about some of those issues related to the 737 as well. But that's traditionally how we do that design process. Is we start from here and then we support the decisions we make with fundamental science. Okay, and that's how we're going to work on this design project. And that's going to be part of that benchmarking analysis. Well, if I need to carry so much payload, I should be able to go out and look at other similar types of aircraft to get an idea about how big those aircraft are, what type of engines they have to carry similar types of payloads. And if your design is way out of the benchmark, right, so you end up with a really different value, either you discovered some really new physics or you're doing something wrong. And it's most likely the latter, not the former. So that's what we're going to focus on first. And we're going to support this by looking at a lot of case studies. Going through the process of taking these aircraft. The Piper Cherokee is the one that we use a lot because That's one of the aircraft that you fly in Aerolab, that you do performance analysis on. You go out and fly it, take that data, and pull it back into your spreadsheets and performance charts. We're going to look at the 737 and 787, and look at some of the issues that the MAX has run into, F-22 and F-35, and then we'll look at some of the UAVs as well, kind of using the Traeger as our benchmark. Okay. Now that's our kind of intro to the course. So from a course overview perspective, are there any questions to start off with? Okay, let's jump right in and talk about how you design. And just so you know, these lecture notes will all be online. I haven't uploaded these yet. I usually try to get these uploaded before we have class. If I'm going to travel, I didn't have a chance to do that since I came straight here Sunday airport. So as you see fit in terms of taking notes or listening, do what works for you. So how do you design an aircraft? Well, first off, what does this look like in industry? If you're working for, either a contractor that's doing some kind of defense project, or you're working to design the next generation airliner, what do you typically have? Well, it's going to be something called an RFP, which stands for Request for Proposal. Primarily, it's going to be a really big, thick document that's going to have a lot of requirements in there. You need the aircraft to do X, Y, Z, over A, B, C, costs so much, do this, all these types of regulations. Probably will have some tables in there, performance charts. What it will not have are pictures of what the aircraft is going to look like. That's what we have to figure out. So you have to use these set of requirements and go back to the design tools that you developed through your career and through your company to figure out then what aircraft configuration is going to be optimum to meet those requirements and how big the aircraft will be. And more often than not, which is one of the things that's really unique about aerospace engineering, which makes it such an exciting field to work in, is you may have to do something new with it. So you may have to project out and say, well, this aircraft is going to be operational in 2025. This is where we're at with the technology right now. For example, in the materials or propulsion or avionics, this is where we think we're going to be by 2025. And this is the stuff we have to develop to get to that point. So it's going to be cutting edge. So that way, by the time these things roll out, they're going to be really the best you can do in these types of systems. Now, you think then, with kind of where we're at, with modern technology and all this history, we've been designing aircraft now, right, since Wright Brothers for 112 years, 117, we'll call it 112, so I've made it through in 20 yet, that we'd be able to, put a spreadsheet or some kind of fancy computer program, and just dump in the supercomputer and say, clicking, here's the stuff I need to do, and not only does it print a picture out, not only print your little model as well. Okay. Well, here's the problem with this. First off, what do we know about basic aircraft courses? Most of the time, when we look at the performance of our aircraft, we're going to be doing what we call steady state performance, where the aircraft is just doing this. It's flying at a constant velocity, at a constant altitude. So, in that configuration, what do we know about the forces? They're equal. It's not accelerating. It's not getting faster or slower. It's not climbing or descending. Okay? Steady state. So much forces have to be equal to 0. So that means our 4 forces on the aircraft, lift, weight, thrust, drag, all have to be balanced. So lift has to be equal to weight, thrust has to be equal to drag. Now, here's where the problems start to come in. Things like actually the aerodynamics, which is one of the more challenging things from a scientific standpoint to predict. That's really hard to do. And while we can't go back to those computers and just say, here, spit out what the optimum design is, because it's really difficult. So I worked with the lead technical fellow of Boeing, and using computational fluid dynamics they estimate that the current growth rate of computer power, which still follows Moore's law, where it's doubling in capacity every 18 months, that they will not be able to do a full aircraft simulation until 2085. Okay? So that means that the experimental photonics, the Ventons, right, they still have a long life ahead of test all of these things. Okay? Now, that doesn't mean you can't do parts of it, or you can do some of it, or you can try to do all of it at a lower fidelity or lower resolution. You can do those stuff in there. But the aerodynamics is actually one of the easier things to figure out in the lift. One of the harder things is things like weight. Why that is because, particularly in 1770, an example of this, is you always want to try to minimize weight. You want your aircraft to be light. We're not building a bridge where you can just throw some extra concrete in, whatever, to make it stronger. We have to make it optimal. So we're designing to make sure the aircraft is not going to fall apart, but just that. Okay? We don't want to put any extra weight in because that's going to impact our efficiency. And that's one of the areas where we kind of have the biggest problem. Now let's instead of blaming the aircraft designers, let's throw this back on the engine company. Let's say, you're working with, let's pick on Rolls-Royce. So your aircraft manufacturer says, okay, we're contracted with Rolls-Royce. They're supposed to provide us this new engine that's going to provide us a certain level of power, thrust, and a given specific fuel consumption for a given event. Okay? And they haven't built this engine yet. Okay? It's brand new. They have to figure out how they're going to take this and integrate it and do everything they need to do. And it comes in heavy. What's that mean? What do you have to do with everything else? So if our weight ends up increasing, what else has to increase? So our lift has to get bigger. Now, if lift gets bigger, what else gets bigger?
Drag.
Right. The relationship is higher. Okay, if we're generating more lift forces with a 3D aircraft, our induced drag is going to get larger. If we just said, hey, our engine's 10% overweight, no biggie, we'll just make our wings a little bit bigger to be able to come at. Guess what? Carry more drag. Carry more drag, what else you have to increase?
Thrust.
Thrust. Okay. Now to get more thrust, what do you need?
Better engine.
And so this ends up really quickly being what we call a death spiral. Right? And so you end up having an aircraft, that's infinite with infinite lift. And that means you crumple up your paper, you throw it away, and you start from scratch. And this is an extremely common problem. Boeing, for example, has been designing aircraft for 100 years, and they did this with the 787. They ended up being heavier than they anticipated. They know what they're doing. Well, they do want to know what they're doing, but it's a difficult problem. Why? Because they're trying to reduce the weight of the aircraft by using composite materials. There's a lot we don't know about composite materials. We built the process. Ended up being slightly overweight. That means we have to fix things. Kind of when you don't want to do it, closer to the end of that design cycle. We don't want to do that. Now, one of the ways that we help combat this problem is we specialize. So we have folks working on the propulsion side, for example, who when they think about an aircraft, they think that it should look like that, right? So we have folks over in the aerodynamics who are like, no, I just want to focus on the best lift to drag ratio possible. And we have folks over here, thinking about, what the people on the ground should be doing, right? We're going to spend most of our time kind of thinking about the overall design, but this aircraft has to be serviced. A lot of the things that we do from the aircraft design perspective, when you come and look at an aircraft and say, oh, why is it done this way? More often than not, you can probably say, oh, it's because someone needs to be able to turn a wrench. So, okay. Not only do we have to design it so it's manufacturable, it also has to be serviceable. Okay? And so you have all these specialists coming in, working on their piece, and really kind of having tunnel vision, but then they have to come together and spread everything out, right? be able to focus on that overall route. And this is what we call the systems engineering approach. We have all these different systems we want to optimize. Now, how many of you have taken the survey in here? So the Survey Monkey survey. Okay, so so I want you to come through and do this so that we can come back and talk about the results from this. And this is really to get your perspective both before the class and then after the class, right? So we can see where we're at. Now, which one of these, out of all those, is most important?
Safety.
We did follow prior minutes. Okay. Do any of you know Dr. Rousey? What would he say?
Propulsion.
What is he? Version of like this. Structures. So what's most important? We're going to use this phrase a lot. Okay. So the default answer, if I ask something and you don't know what the answer is, this is what you're supposed to say. Okay. It depends. Okay, which basically means, oh, you need more information to go through it. And we're going to use this a lot when we come in and talk about things and say, well, which way should we go? Right? We have design A, we have design B. What are we going to focus on? Aerodynamics or structures? Propulsion or control? It depends. So now when we come back and look at that perspective, it's kind of something more like this. Okay? 2A, right? Focus on that 2A. You'll see that. All right. So it's hard to do this. And this is why we can't just, have a nice little spreadsheet where we can plug in some values and we end up with an aircraft design. Now, not all is lost, right? There are lots of things that we can do with this. I think I'll be able to wrap that up. We have a lot of tools we can use. These are two that we're going to start off with. XFlow, you should have used this in Dr. Davis' class. We're going to do more about that. Dr. Avery will talk about that on Friday. So XFlow is going to be a really important tool for us. And then we're going to use another one to introduce the asset design called ESP for Vehicle Sketch CAD, which is a way that allows us, it's basically like a simple CAD that's specifically for aircraft designs. So that way we don't have to worry about kind of focusing on like, making a gear. It allows us to treat a wing like a wing and scale things up and down with wing like. So we'll come back and spend more time on each one of those. And I will provide some videos offline for you to come in and learn how to do this outside of class as well. So we'll have certain resources to be able to refer to. Now, let's look at this. Will there ever be a single design solution? No, because there's always going to be options that you can pick at. So here's I'm going to start off with an example for this semester. So this is the 1950 long-range strategic nuclear bomber. We had the British solution, we had the U.S. solution in terms of the Avro Vulcan and the B-47, respectively. And you can look at the history of each one of these in terms of how they evolved. The engineers didn't sit down one day and say, hey, this is what the B-47 is going to look like. They started off with this and then essentially evolving it until it came out with this in April 1946. Why do they call it the B-47? They first flew in 1947. Yeah, it's real rocket science. Right? Question, why do they call it the B-52? Why is it the B1 called the B1? It's nothing to do with it. It doesn't work all the time. Right? Now, if you look at the Avro Vulcan, right, it's a completely different design aircraft. We have this, which we can consider what we call the traditional tube and wing. It's a real, again, fancy name for a tube with a wing attached to it. And then we have this flying wing design, which from an aerodynamicist perspective, you look at this and this is sexy. This is kind of, utilitarian. So you can look at for example, the max takeoff weight. more than 2,000 pounds, right, in terms of their mission. Their wing areas, however, very different, so very different aerodynamics from one aircraft to the other aircraft, okay? Payload weights, also the same. The drag ratios, different for both of these. And so you can look at these and say, well, which one is a better aircraft? That's the answer.
It depends.
Depends what you're looking for those two aircraft, okay? One of the issues, for example, with the B-47 was its takeoff distance. So they usually had to augment its capabilities with takeoff by having, things like radar or radar systems in order to be able to get things off the ground, okay? So that was a pretty, days when we didn't worry about so much, but Avro Vulcan was flying up until I think 2 years ago when they retired the last one. These being a pretty sexy aircraft. Now, in the end of the whole scheme of things, which design won? And you come back and look at the B-47 here, right? And you compare that with configurations for the Boeing 707. Which is the foundation for the modern airliner, and a more modern version of the Airbus A340, and you can see, wow, those all look pretty similar. Okay. So you can say, hey, they probably got 90% of the stuff right in terms of optimizing the aircraft design with that basic B-47 configuration. And this is why we can go back to this and use this as a good starting point to say, hey, if I'm designing this aircraft, do I need to start from scratch? No, I could start with one of these points here, just like they did. They started with a modern aircraft design, modern for them, and then evolved it from there to meet the new mission requirements. Okay. Now, is that the end of the whole story? No. You go back and look at the Avro Vulcan and say, well, we still have flying wings now. B-2, for example. Okay. It just has a different mission. So instead of having that flying wing primarily for dynamic performance, that flying wing is there for radar cross-section in this case. Okay, but still foundational perspective from a lot of this. Now, where do we start with this? So this is where I want to kind of end up at with this piece. As I mentioned before, there are two ways you can do this. One for the science piece, called the ground-up approach. One is benchmarking, called that empirical. What do I mean by empirical? The dots. I plot, I draw a line, hopefully I end up in a nice way. Look at the speed with a high R-squared value. If I do great, I have a good correlation. I can use to at least interpolate. Extrapolation, I use extrapolate. How do you do that? But that's what we're going to start off with our basic. Now, however, we also want to make sure that we explore a lot of these design spaces as well. This is a good example of this. For the Vertical Lift Society, they basically keep track of all the different types of solutions people come up with over the years of vertical lift operations. Any idea what they call this chart? Yeah, it's cycle. Either referred to as the wheel of misfortune or the wheel of pain, because more often than not, this is just like Thomas Edison said, oh, I haven't figured out 10,000 ways to fail, I figured out 10,000 ways not to build a light bulb. And most of these are like, yeah, they typically don't work. So you see lots of about this. The Joint Strike Fighter is a good example of that. Right? You come back, look at the Joint Strike Fighter at the Lockheed Martin. They basically started off using the F-22. Why? Because that's what they had. It's where you use this. Boeing, McDonnell Douglas, they had completely different designs when they were coming back and looking at this. So when we come back and look at the F-22 and F-35, we'll revisit these. Now, I want to do this as kind of a final piece of where to start. This is a really simple equation, but it's a great place to start off with. We're going to evolve this to the great flight diagrams. I'm ready to talk a little bit about this on Friday. I want to start this really easy. So let's think about this from a perspective of thrust has to be equal to drag. Level and steady flight again, right? So we have this aircraft, and we want to be able to fly in level steady flight. We have to design for that. If we can't get that to work, we can't get anything else to work. So it's going to be our point of departure. Yeah. Really easy equation to come up with. We say thrust is equal to drag. Okay. Then we take that drag side and multiply it by weight over weight. Because it's equal to 1. The level of steady flight, lift has to be equal to weight. So we replace one of those weights with lift, and we rearrange that, and we get thrust is equal to weight divided by the drag ratio. This is exactly the same thing as that over here. Thrust is equal to drag. We just used algebraic trickery to be able to get into that one. That is the simplest equation we'll have this semester, but it's also really, really powerful. If you want to know how big your engine needs to be, tell me two things. How heavy your aircraft is, what's your lift drag ratio. Now, those two things are really hard to predict. So that's where your challenge starts to come into play. Then you throw on top of that, well, how fast you want to fly. So all you have to do now is just multiply that by velocity. Now you know the power output, or the power output required. Put all that together, you figure out the thrust, you figure out the power for your cruise velocity, and that tells you a lot of. That's a really good starting point for your aircraft. So some of the things you want to do in your benchmarking as well, how heavy are other aircraft that fulfill similar types of missions to the aircraft you're design? What's your lift drag ratio? How fast do you fly? What type of engines do you use? You can start to put all this together with a really simple equation to start to get some ideas about what that design is. Okay? All right, so real quick before the break, questions? Do we have any questions about anything? Okay, yes, go ahead.
You mentioned that like in the very beginning of the class that we took a survey
Yes,
about like our favorite movie and all that stuff.
yeah.
We have not done that.
That's right, so that's a PowerPoint file.
Okay.
If you go to Canvas, you'll find that under administration, so there'll be a single slide of the issue called survey
I don't know why I forgot about that.
Download that, edit it, upload that, that's homework 0.
Okay.
Okay, that's 2 live time.
And so there'll be other homework problems that are due next year. Got it.
Like, not student this